And we have a number of additional people coming, so don't worry, these seats are going to be full, and I apologize actually that it's a bit, it will be a bit crowded, I think, later on in the afternoon. So my name is Pam Pearson. I'm the director of the International Cryosphere Climate Initiative, and it's my great pleasure to welcome all of you here today. This is an event focused on the cryosphere, regions of snow and ice, where climate change is showing itself faster and more clearly, of course, than anywhere else. And it's appropriate to meet here on the margins of COP19. There's some history to this because part of the forming, actually, of ICCI came when we invited Dave Carlson, who was then the executive director of the International Polar Year, to come and speak at the Bonn meetings, which occur annually as part of the negotiation process, and had him give a little bit of an overview of some of the first results of IPY. And I thought the questions, you know, from some of the negotiators who I knew personally, this was in 2008, were reasonably good. And seemed to show that they were up on top of some of this research. And his first comment to me after the side event was, my God, these people know nothing. You know, a lot of this has come from even the New York Times. Don't they realize how quickly things are changing, what the latest research is? And that was, in a sense, when the germ, the seed was planted to form ICCI, but also to begin having these kinds of events at the climate negotiations. And since then, I think we have had side events for delegates to the COPs at every COP and at almost every Bonn meeting. We might have missed one summer, but then we had it in Tianjin in China a couple of months afterwards. But at the same time, one of the things that was very, very clear to us from the very beginning was that we were focusing on such small pieces of what was going on in the cryosphere. And there are so many different regions and so many different people working, and so especially given some of the developments since IPY, which have been fairly extensive. We also had the On Thin Ice report, which you'll hear about a little bit later, which also has a survey of what's going on in different cryosphere regions. The time felt right to try for a full-day event, and for those of you who have not been to these COPs before, this intercessional Sunday, the Sunday in between the 2 weeks of negotiations, is a traditional time to have these full two events to delve a little bit more deeply into new science or into, you know, developments that have maybe a broader area of interest. The delegation rooms are closed in most cases, and so it's a good time for delegates to get that extra bit of something new. So that's why we decided to try this year and to focus on the different regions. I don't think it surprises anyone here for me to say that climate change presents more extreme challenges in these regions than anywhere else, and it's not just because of the rate of change. The temperature is rising twice as fast in most of these regions. It's actually rather striking that you have, in some ways, some of the same sorts of rises going on in alpine regions as you do, say, in Antarctica or in parts of the Arctic. But also they bring a great deal of risk. We have the risk associated with potential Greenland melt, for example, the potential disintegration of the West Antarctic ice sheets. These are things that we can't predict, but we know that we're already within the range of temperature and carbon concentrations in the atmosphere where this has occurred in the past. And so more than anything, work on the cryosphere is really work to constrain that risk to some degree and to understand these processes while we have a chance to do so. Like a lot of things in climate change, you really won't know for sure until the event actually takes place. The COP negotiations also, they're very strictly oriented towards trying to get to a certain point by the end of this century, by 2100. And of course, the cryosphere clearly is on a much more near-term schedule. We're looking more at changes by mid-century that concern people. And we'll touch on some of these aspects today and on potential appropriate mitigation and adaptation measures. So we have one welcoming remark at this point that is a video cast, but before that, for those of you who are in the room, this is being web streamed as well, and we'll be accepting questions both from the floor and from people who are emailing questions, or we're actually on Twitter at this point, and so I am not a tweeter, but if any of you are, feel free to do so. The bathrooms are out and to the left. Coffee will be served continuously. Please, this is informal, feel free to go out whenever you like. We will stick fairly strictly after this to the schedule due to the streaming so that people can tune in when there are sections that they're interested in. And so I will go ahead and begin with the video address from one of the co-initiators, I think you could say, of a report called Melting Ice, which came out in 2009 and was also a summary of changes in the cryosphere as of this point. It was initiated by the then Norwegian Foreign Minister, Jonas Gahr Støre, and Al Gore, and we have former Minister Støre to give an address at this time, so I'll get that video started.
Four years ago, as Foreign Minister of Norway, I had the honor to chair the ministerial meeting of the Arctic Council in Tromsø. In conjunction with that meeting, former Vice President Al Gore and I invited experts from 5 continents to address the threat from rapid climate change in cryosphere regions. 4 years ago, as Foreign Minister of Norway, I had the honor to chair the ministerial meeting of the Arctic Council in Tromsø. In conjunction with that meeting, former Vice President Al Gore and I invited experts from 5 continents to address the threat from rapid climate change in cryosphere regions. We call that event Melting Ice, Regional Dramas Global Wake-up Call. And yes, the backdrop was alarming. Snow and ice are melting far above normal seasonal changes, even at the coldest places on the planet. In the Antarctica, the Arctic, Greenland, the third pole of the Himalayas, and other glaciated areas throughout the world. Leaving Tromsø, the Vice President and I decided to invite leading scientists to summarize what we knew about how fast these changes were occurring. All of this knowledge was presented in the Melting Ice report published in time for the COP15 in Copenhagen later in the fall of 2009. That report, Melting Ice, brought together the research of hundreds of cryosphere scientists, laying out a clear message of unprecedented change in these regions and the urgency needed to address them. The dramatic evidence of the report was that the trends we observed earlier in the last decade were proved to be not only real, but even more dramatic, with less ocean ice, more melting snow and ice from the poles, and alarming scenarios from rising sea levels towards the end of the century. Today, 4 years later, we know that scenarios have shifted into observed facts, and we can confirm in November 2013, with even more certainty than in November 2009, that we know enough to act. The need to act on the global challenge of reducing greenhouse emissions, but more specifically acting for the sake of the North Pole and the South Pole and the high mountains. We need more decisive early action on short-lived forcers like black carbon, and we need more effective assistance to those affected across the world by these changes, the affected populations. The 2009 ministerial meeting in Tromsø saw the very beginnings of work on the challenge from black carbon. The Arctic Council appointed special task force, and a variety of initiatives have been launched in different international settings. Much has happened since then. The recently released IPCC report documents and confirms many of these observed and projected changes in the Arctic, Himalayas, Antarctica, and other cryosphere regions. I am pleased that you have IPCC representatives with you today to report in greater detail, and I'm pleased that this critical issue is on the agenda of the COP19 in Warsaw. The Arctic Council, with its permanent secretariat now placed in Tromsø, has also moved forward and is considering finalizing an agreement aimed at helping Arctic nations decrease their black carbon emissions. This is good, because this we know. Black carbon is a potent emission contributing strongly to warming by all the black spots left on the white surface of the polar and mountain regions. But unlike CO2, black carbon can be dealt with much more swiftly. It is a short-lived climate gas. Improved industrial processes can help bring emissions down, and a lot of this is low-tech, not necessarily high-tech, like moving to scale with clean cook stoves. Much has also happened beyond the Arctic, in more global forums on black carbon and other short-lived climate pollutants, especially work by UNEP and the creation of the Climate and Clean Air Coalition. Norway and Norwegian civil society organizations are active in supporting work at mitigation and adaptation of vulnerable mountain populations, especially in the Himalayan region. Because of this history, I was encouraged to see the publication by ICCI and the World Bank on the On Thin Ice report, which brings these two strands of work together. On Thin Ice updates the work of the Melting Ice report we produced in 2009 in terms of research into changes in the cryosphere since then, since 2009, during these 4 years. It then goes on to model how measures aimed at pollution might slow these changes. So now we start to know the building blocks, and I welcome this work. It makes us wiser, and it makes us a little bit more hopeful that we can produce change. The modeling shows that all of us have a role to play in decreasing these pollutants, from controlling open burning in fields and forests, to improving wood stoves in Northern Europe, like my own country, and cook stoves in developing countries. And as we recall at every crossroad, this is a potential doubled win, because all of these measures will also improve human health and agricultural yields at a time when food security already is under pressure from climate change. Dear participants, I am gratified that the work of Melting Ice is continuing today through this global network and the many organizations and researchers participating in the Cryosphere Day, and through you who are joining the event via webcast around the world. As we and our children in my country eagerly wait to see the first white snow fall over plains and mountains, I wish you, working hard in Warsaw, all the best in your discussions and endeavors at COP19.
Okay. So I guess I should, at this point, declare the first Cryosphere Day open. And it's my great pleasure to open this, to have with us today Dr. Georg Kauser from the University of Innsbruck, who is the lead author for AR5 Cryosphere Observations chapter, to talk a bit about, well, to talk a lot, I hope, because we have some time now, and take questions on the results of AR5 as they pertain to the cryosphere. So, Dr. Kauser, please.
Thank you very much. And if you can hear me this way, I would just...
I think for the streaming, can the streaming people hear? No, you need a mic, I'm afraid.
It's green now. Oh, yeah. Oh, now I can hear it myself. Thank you very much, Pam, for inviting me to this Cryosphere Day. And for those of you that had attended already the yesterday's session back in the conference center, it is a bit of a repetition, although I try to extend a little bit to get a little bit into more details. So I had the pleasure, honor, and the burden to be a lead author of the first and then also for the 5th assessment report. And there I was together with a bunch of other colleagues responsible to assess the observed changes in the cryosphere. We also were interacting with other chapters that dealt with the energy budget of the Earth system, and also those that dealt with the sea level rise, particularly with those, but also with those that did the detection and attribution chapter, so to understand why those changes are, or to which drivers we can attribute these changes. Now, to start with, I think we have to just tune ourselves into something which is not just a static topic we talk to, which we can deal with statistical approaches. We have a highly dynamic system which we have to deal with. And this figure here, it shows actually the hurricane and typhoon season in 2005, autumn 2005. But it shows very nicely the dynamics of the atmosphere, tracing the vapor in the atmosphere, but also the ocean, which we cannot see here, is a highly dynamic system. So the entire thing moves a lot. Now, sorry, I better go back. Now, as any other system, it is intended, or it intends to be in an equilibrium state with in terms of energy. So all the energy which comes in should also go out. Now, if you disturb that for a little while, like with a volcanic eruption, the system itself takes a little while and then it is set back to an equilibrium again, or kind of around an equilibrium. But if we go and disturb this equilibrium in a sustained way, then we have to expect changes. Changes not only in single statistical values, but also in the entire dynamics. Now, what was the change in this, or what was the disturbance in that? So we did disturb it from the pre-industrial area, whenever that started, or how long ever that went. Until 1950, we had a disturbance, a man-made disturbance in the system of 0.6 watt per square meter. In 1980, we had already 1.25 watt per square meter. Now we have reached 2.3 watt per square meter. So that is it's a permanently increasing, due to our emissions, permanently increasing disturbance of the energy balance of the entire system. And you can imagine that that causes a lot of things, not just warming. Now, where does this energy go these days? It goes to 93% into warming the ocean, but warming the ocean means also getting into the dynamics of the ocean. 3% warm the land, 1%, only 1% warms the atmosphere, including changing dynamics of the atmosphere, including also changing in the water cycle. And 3% are used to melt ice. Let's go first to the biggest bunch of ice we have got, which is Antarctica. It's very thick and stays on one of the poles, or on a continent around one of the poles. And the colors show you the observed changes of ice mass in Antarctica. So this is the entire period 2003 to 12. It's split into 3 to 6 and 6 to 12, and you see an increase of mass loss, the red colors, in West Antarctica. It's the peninsula plus this Amundsen Sea sector of West Antarctica. There is actually accumulation or mass gain over a series of parts of East Antarctica. But what is the reason we do not have surface melting in Antarctica? Melting is not what occurs there, at least not on the surface. So if we look at the mass surface, the mean surface mass balance between 1989 and 2004, we see no yellow or red colors. It's all blue. Actually, we have the highest accumulation in the periphery of the ice sheet, and in the interior, as we know, it's kind of a desert. On the other side, we have a lot of outflow. This is the mean ice sheet velocity fields over a couple of years or 2 years here. And we see with the blue-red colors the highest speeds, the highest velocities, and they are where all these huge ice masses are squeezed out into these ice streams, which then most of them, or many of them, end up in a floating part, which is the shelf ice. Here we have a huge shelf ice, here we have a huge shelf ice, but also here and here around we have shelf ices. If we add those two things together, then and then do kind of I mean, the time periods are a little bit different, but we see that we have a loss or a thickness change, particularly in that region. A little bit here too. But what is the reason? It is not melting. And it is in fact that there is melting going on, but due to the dynamics of the ocean, we get warmer water masses underneath these shelf ices, and they melt, they thin from below, not from the top. But since they are floating, they also change their exposure to the surface or above the sea. But what happens, what is the most complicated thing, is that you start moving this grounding line backward, where the ice touches the ground, which is underneath the sea. And if you move that back, that whole thing becomes unstable, or at least allows for an accelerated outflow. And this is what we observe now. And some of these ice sheets, ice shelves have already broken off. For instance, 2 days or 3 days ago, a huge piece of 30 by 50 kilometers has broken off from Pine Island, or this Pine Island area, again in the Amundsen Sea. So, and behind that, the ice flows or the ice streams are accelerating. They are losing more mass due to the dynamic responses of the ice sheet. So the dynamics of the ocean interact with the dynamics of the ice sheets, and the ice sheets altogether lose mass. Actually, it is Antarctica. In Greenland, we have a different picture. We have these red colors here in the surroundings. There's a lot of melting, surface melting going on. But there we have also these high-speed outlet glaciers here. And altogether, they show a thinning of the ice on the Greenland island, or on Greenland. Now, the dynamic response plus the surface melting are, or they make up 50 and 50%, so it's half-half for the time being. And we see here between 2003 and 2006 less mass loss than we have seen for the next 6 years, 2006 to 2012. And that is mainly also, this increase is not only because there is an accelerating outflow due to this loss of ice shelves in the periphery, but it is also because the melting has gone higher and higher and higher. And we had actually 1 year where also on Greenland summit we had melting conditions. So there is melting on the surface, but also this dynamics. Now, if we look to the mountain glaciers on Earth, it is a highly scattered picture, and that's all what I wish you to take as a message here. We have here subdivided the whole thing into 19 regions, and these are the 19 regions, and apart from Central Europe, which is actually the Alps, which show a convergence of the different methods and the different timelines we have, there is also one modeling on top of that. All the others, they show quite a scatter in what we know, particularly here in the Himalayas. This is this here. Now, for that reason, we have pushed a group of contributing authors to look closer to that, to do a kind of a comparison of the different methods and to come up with a reconciliation of what we know at least between 2003 and 2009. And this is now again these 19 regions. Actually here we have grouped 3 together. So, and the huge circle here shows the aerial extent. It is in 50,000 square kilometers here. The bluish color says these glaciers are terminating in oceans, they are terminating in water. They are exposed also to these dynamic responses, which I have explained for the ice sheets. The green ones are all land terminating. The yellow dots are all the glaciers we know one by one. We see the loss of ice in gigatons per year. This is a rate, gigatons per year from Alaska, for instance, here from the Canadian Arctic, from the periphery of Greenland. It's not the ice sheet. Here from the periphery of the ice sheet in Antarctica, which is mainly the peninsula, Patagonia, the tropics here, which include also the Irian Jaya and East Africa. And the Himalayas, of course. But if you look to this pinkish, or I don't know how you can see, which color you see, it's kind of a pink fringe around this red dot, that tells us about the uncertainty. And we have still among the biggest uncertainties here in the Himalayas. We may have time to talk about in the afternoon. Now, altogether, if we look at the summary of that whole mass loss from continental ice, then we can look into the contribution to sea level rise. And the biggest contribution to the observed sea level rise, which I have here, is still the ocean warming, the thermal expansion. But then come the glaciers with 28%. Greenland and Antarctica together make up 20%. But Greenland and Antarctica are catching up. These are the glaciers contributions between 91 and 2010, 11, 12. We have different time series. They are catching up while the glaciers are more or less constantly contributing. And then comes the land water storage, which is basically the depletion of groundwater into irrigation and then comes into the water cycle. Sea level rise has accelerated. If we go over the entire period, 1901 to 2010, it is 1.7, then we go up to 2 millimeters per year, and we have now reached a rate of 3.2 millimeters per year. Snow cover in its extent on the northern hemisphere in spring goes back, it's another indicator, but particularly the Arctic summer sea ice extent goes back in extent. But it not only goes back in extent, it also goes back in thickness. I do not go into all the details of that, but the thickness goes from year to year, it becomes thinner. So it's really, that part is really thinning. And the average length of melt season goes up from a little bit above 100 days. We have reached already 125 in average. It goes up and down, of course. So this traces us back to the immediate impact of the energy which we put into the system. On the other side, we have also a lot of dynamics in the sea ice. Sea ice is a thin thing which can float around on the surface of moving oceans, but can also be heavily driven by wind. And if we look into the Arctic sea ice, that is kind of a big pool surrounded by continents or islands or whatever, and it turns around here, and there are huge storms which, for instance, have contributed to these lowest values of sea ice extent, just for pushing this ice to the southern fringes of this basin. On the other side, we have Antarctica, where we have little, if even, so we have a little increase of sea ice extent. And that is also due to people try to explain it for the time being. It's not yet studied in full detail and full length. But it seems that not this drift of ice close to the continent, but the counter drift around Antarctica pushes the sea ice toward the continent. And it is not that energy and melting make the main role, but it is a changing dynamics around Antarctica, atmospherically driven mainly. We have as a last indicator the permafrost and the changing of the active layer. I learned just half an hour ago that I had a wrong terminus here. Active, I'm absolutely not into that. I report what others have put together. It's a lot of different stations in the Russian Arctic mainly, and they show a changing of this seasonal melting on top. Altogether, it's now about 30 centimeters thicker than it was in 1930. So we melt that more deeply every year. Now, how is this going on further? How is it going toward 2100? And there are these representative concentration pathways which are expressed in where we get with this radiative forcing if we behave in different ways in the future. And those four scenarios are those with which all the projections are done in AR5 in the newest IPCC report. So there is one which says 2.6 watt per square meter, but we have already 2.3. And that one is the only one which allows us to keep this 2 degrees Celsius target as the balanced temperature which we may reach if we get that into the atmosphere or all the changes. It's not just the atmosphere, it's also land cover changes and so. A much more probable but also very difficult to meet target would be 4.5 watt per square meter. Much more probably is we go toward 6.0, and if we do not very much, just a little bit, to change all our impact on the climate, then we go straight toward 8.5 watt per square meter or even more. And that is far beyond of this slide. Now, people have calculated either all different colors here, different scenarios, which are the same colors, the worst one, the 8.5 or the 4.5, the 2.6 here, and have shown, for instance, or have extended that in projections of the snow cover extent on Earth. So you see there is an extent even with the 2.6, but there is a strong one with the 8.5. If we go to near surface permafrost areas, they may decrease, or they are expected to decrease, even if we go along as we do right now, or just slightly worse. But they decrease very, very strongly from today, about 15 million square meters, down to, with the uncertainty, even almost to zero. Similar, the northern hemisphere sea ice extent, which also can go down to zero long before we reach 2100, or can stay a little bit above, but they will be much less than before. And here is just shown how the area extent. It's basically the same, but in an area distributed extent, what the scenarios are. Ice sheets and glaciers are summarized in what the sea level rise will do, and we go into sea level rises in the least dangerous scenario up to about 40, 50, basically half a meter higher than we have been in the year 2000, or actually as an average 1971, 2000 to 10. But if we do as bad as we can, or as bad as we do now, then we get up to something which is 80 centimeters or almost up to 1 meter. Just to close with that, what are the glaciers doing? Glaciers do not contribute constantly because they are getting smaller and smaller, and less ice is there. And there is a projection which even goes beyond 2100. It goes to 2300. And we see all the scenarios tell us that up to 2050, the glaciers still increase with contributing water, because there is still a lot of ice out. Even if the Alps may be, glaciers in the Alps may be gone by then, there are many, many others and biggers out there. But then, and this is now different colors, I have to say. This is the 2.6, the red one this time is the most favorable, or the most gentle scenario. Then we would get around 2050 with most glaciers which still remain by then into an equilibrium, and they would contribute less and less and less. The next scenario, and then comes this 8.5, which is the purple one, which would allow us to go until 2100 in order to have major contributions from the glaciers. And then they would be gone, but there would be much less left than in this case. So in this case, many regions would be without glaciers. So I thank you very much with that, and I hope there are questions, or if there are, we have time to answer them. Thank you.
Both of these work? Okay, so I guess I'll be the microphone runner, and if I could ask one clarifying question about the RCP scenarios. They assume still a peak, yeah? And then after that, the decline?
They assume a peak on all of them.
You need the mic, yeah.
All of them assume a peak, which is hardly visible in the 8.5 one, but even there is a peak, and that's the peak in population. People think that the population is going down after 2050, roughly, or mid-century. And there are obviously strong indications for that, but that is not really the topic for a glaciologist to answer.
Yeah. And maybe this isn't a topic for you to answer, so we can ask it for permafrost. But for the permafrost slide that you showed, in terms of the increasing melt there, do we know what that corresponds to in terms of carbon releases or methane globally? We don't know. Okay,
in the
IPCC
report, we had just one paper available, which was on one single site somewhere around the Baikal Sea, I think, or somewhere in the Russian Arctic, where one study showed that there was an increase of methane exhalation. But that's the only point where it was measured, and that is not enough to really say it happens already. But potentially there is a lot of methane in it, and we will hear later much more and more details about that.
So other questions, please.
Thank you. Lars Norberg, ICCI. Sometimes when I discuss with the skeptics, I hear an argument concerning the melting of the ice from below, that they say that that has nothing to do with anthropogenic sources. It has to do with radioactive decay and geothermal energy coming from below, and to melt the ice from below. And well, I hear that argument, and it's not very well substantiated, but maybe you have a comment to it.
That's interesting to hear. So you obviously have different skeptics, or skeptics with different arguments. I haven't heard that yet, but just instantaneously, I would say the geothermal heat is, and the radiative energy from the interior of the Earth is something which is more or less constant. It is spot-like changing, but as a whole, it is more or less constant. And what we see here, so that happened also 100,000 years ago. And what we see here is something which is not only an acceleration of melting from below, but it's also linked to ocean circulation patterns which people measure and model, and they know exactly that there is a penetration of warm water coming in, and they can also trace it back where it comes from and where it's heated up by the energy, the disturbed energy budget, so to say, of the Earth. So that's what I would answer, but I have never thought about that. I never heard that. I've heard a lot of different things, but not this one.
If I reply to them similarly, then they say it's not constant. Look at, for instance, Iceland. Sometimes the energy flow is very, very low, and sometimes it's very, very high. So it is fluctuating. That's a point I hear.
Yeah, that's correct. Locally, it's not constant, and this is same argument turned around and as valid as the other one. Yeah.
Other questions?
Guglielmin from Insubria University. Now, which is the accuracy of the mass balance in Antarctica?
I best go back. I think I have the numbers here. No, actually, I don't show them here. It is very close to the amount of what the mean shows. So there is still a big uncertainty, and mainly also coming from East Antarctica. There is the knowledge about the accumulation and the changing accumulation there is not very satisfying yet. So it is a small amount coming from Antarctica. It is about 10% to the total of sea level rise, and that is. Has an uncertainty which is as large as in other areas, or even larger than in other areas. I would have to look back at. I have not the numbers in mind, but you can look at it. Very easy. This is a very easy here website name, Climate Change 2013, and there is the summary for policymakers, and there are the real numbers there.
Other questions? Okay, we're almost toward the end of this time, so we're going to make a switch now. And as you look at the program, you can see that we are doing the different regions at different times. And up here in front are some of the organizations that have helped to arrange this day, which I really want to recognize as they come into their sessions. For the Arctic, it's primarily the Arctic Council's Arctic Monitoring and Assessment Program and IASC, who have gotten some of their researchers together to speak to us today. So if you could come up, then we'll do a switch out and we will move to some of our regional specific sessions. And then after the Arctic session, we'll have a 15 to 20-minute coffee break.
Okay, good morning. My name is Lars Otto Reiersen. I'm the executive of the Arctic Monitoring and Assessment Program. That's the working group under the Arctic Council that the previous Minister of Foreign Affairs spoke about, the Arctic Council. So our mandate is to monitor and assess the Arctic regarding the pollution and the climate change and the effects on the ecosystems and the humans. So in the next hour, we have a session here together with the International Arctic Science Committee and the World Climate Research Program, CLIC. We made together an assessment called SWEPA, the snow, water, ice and permafrost in the Arctic. That was an assessment triggered after we presented the Arctic Climate Impact Assessment in 2005 that said there were huge gaps in the Arctic. We were lacking information about the cryosphere, the Greenland, the glaciers, the permafrost. So we put together an international group of scientists working in the Arctic and produced a thick scientific report back in 2011. And based on that, we made this thinner report, which we hope that could convey the message to the politicians. So lots of pictures and big letters, but even this was too thick for them, so we are making this very thin report and hope that can reach the politicians with even bigger pictures and less text, and this is bringing through to the politicians. So what you will have in this hour, we have asked two of our scientists to come here and speak, and I shall just give a short introduction to what we are covering. The snow, water, ice and permafrost, this is the science report. Up here on the left is a thick one, this overview report, and then some thin one that we're handing out. There are videos showing what's going on in the Arctic, interviews with the scientists, and all of this is on the web of AMAP if you're interested. Greenland was mentioned by the previous speaker. When we did the study, we didn't have good runoff data from the Greenland. So what the scientists said here is when you're going back to the 90s, Greenland was in balance. What was snowing on Greenland was more or less equal to what was running off Greenland or coming out with the glaciers. Using all the data from the satellites, you can see here over the data indicated there's a clear netto runoff. So when we published this in 2011, the netto runoff of Greenland was approximately 200 gigatons of water. So what is 200 gigaton? That's 1 meter water over Australia. And the latest figures, this is the figures a year later, coming up to close to 300 gigatons. So that's a substantial increase in the runoff of Greenland. And that's what we also learned from the previous speaker, that Greenland, the sleeping giant in the north, has started to contribute to the sea level rise much more than before. One thing that hasn't been too much in the media is the snow change, that you have a change in the snow. Most journalists are focusing on the change in the sea ice, and we'll learn more about that in the next speakers. But in the snow, there's a clear reductions over the last decades of approximately 3.4 days per decade, especially in the springtime. The runoff of the water with the big rivers, some of the largest rivers in the world are running into the Arctic. Looking into the data available, you clearly see an increase in the runoff in the Siberian rivers, the Ob, Yenisei, and Lena. And we are now working a special work together here. We're trying to put in a study together with the Russians and the GEF, the Global Environment Facilities, to do a detailed study on the consequences of the increased runoff of the Russian rivers, both locally in Russia, but also on the circulation in the Arctic Ocean. And there's also initiated a new project to look into the freshwater budget in the total Arctic, that also will be ready within 2 years' time. An interesting thing in the SWEPA was the first time to look into the feedbacks, how the climate change, together with other cryospheric components here, the sea ice, the Greenland ice sheet, but the other forcing here you have the surface albedo change in that, the water vapor, and we can see the positive feedback here between the climate change and the surface albedo, that less snow, less ice is increasing the accumulation of the heat. And this is a huge research area we're now going into to understand more about these combined effects that's going on. Then the black carbon, we were asked back in 2007 to start looking into the black carbon, because we got this information that the force from the black carbon and the ozone in the Arctic might be as strong as the climate change from the greenhouse gases. So this is a figure from the presentation, the report in 2011, where we have the total force from the whole world compared to what the Arctic countries. It's much less, but its indication in that report is that the closer the source is to the Arctic, the more effect it has on the snow and ice melt in the Arctic. So what we're doing now, we are preparing 2 new reports related to the short-lived climate forces. There's one specifically on the black carbon and the ozone, and one on methane. And these reports will be ready in May 2015. So this is just from a paper from one of the lead authors of the work on black carbon. On the black carbon from the flaring, the gas flaring from oil and gas industry, indicating that there's a clear, huge contributions from the flaring. Maybe up to 40% of the black carbon in the Arctic is coming from the flaring from the oil and gas industry. Here is Hibernian out of the gas field out of Canada. There are some spots you can see where you have, but it's very interesting new studies just republished by this group. And then the methane. This is a publication from a Russian scientist in 2012 showing these increased emissions of methane from the shelf area. This is a huge area to go into to do the more into the scientific work. The change in climate, normally, we have a cold air coming down from the Arctic over Europe, over North America. We have this dome of cold water, cold air. What people experienced during 2009 and 10 is that you have extreme cold, January, December, November. So people say, well, there's no climate change. It's cold as never before. And that is partly linked to what's going up here in the Beaufort Sea. Before the ice is covering, it looks like there's a split now in the dome. So you get this cold air down over Europe, and the warm air is coming up over Greenland. So that's an area where Jim Oland and his group in Seattle is working to follow up on this part. The latest report we have, also linked to the climate change, is the sea ice, not the ocean acidification. We have been released this report in May this year, and it came as quite a big surprise for many that the ocean acidification so far has been focusing on coral reefs in warm water, but it looks like it's going much faster in the Arctic. And that is due to that CO2 is accumulated more in cold water, that when the sea ice is retreating, more water is open for accumulation of CO2, and then we have all the carbon coming out with the big rivers. All of this together shows that we have already ongoing a rapid ocean acidification in the Arctic, and it's the primary driver of this is the CO2 emissions from the humans. So we see a change going on in part of the Arctic, and the Arctic ecosystem is rather vulnerable because it's a very simple food chain. There's not too many species, so if one of the species are affected by ocean acidification, that might have secondary effects on the food chain. So this is a report, it's just coming out with a scientific report from the press. So this is where we are now. There's a lot of activities going on in the Arctic, industry within there, opening to the oil and gas, to the mining, to the shipping. So what is the combined effects of all of this increased activity in the Arctic? So that is a new assessment we're looking into here to have ready by 2017. Who will be the winner and who will be the loser is the question. Okay, I'm going to give the floor to the next speaker. The Arctic is a barometer of the globe, indicating what's going on pollution and climate change. So maybe Margareta, is you the next one, or? Is Turkey? Okay, sorry. Yeah.
I think it makes sense for all of you to be up here as well.
I don't.
So should I do it now?
Ja.
Okej, tack. Och ska jag sätta...
Yeah, it might be easier for you to sit up here. I mean, if you like standing down
I-
here. You love to move.
She loves to move.
Yeah.
But is it, I just want my... Thanks.
That's it.
Good morning, everyone. It's a great pleasure for me to be here to talk about what my family refers to my third child, permafrost. Permafrost in a changing climate. So what? I will start from the beginning. I don't know if you're all permafrost nerds like I am, then you know this out of the top of your head. If you're not, then I think it is good to have some sort of introduction to know sort of what is permafrost. And yeah, we start from the beginning. So what is permafrost? Well, permafrost is just a definition that someone has invented, but it basically describes frozen ground. And the definition is that it has to be frozen for at least 2 or more consecutive years. And if we look at a profile from the surface, here, downwards, we have an active layer on top of the permafrost that thaws and refreezes. And this is what you were showing, that this has increased in Russia, for example. And underneath this area, this layer that thaws and refreezes on an annual basis, we have the permafrost. And permafrost can be anything from a few decimeters thick, but it can be down to 1,400 meters thick. So we're talking about a lot of area that can be frozen. And of course, underneath the permafrost, you got unfrozen material. Now we are all agreeing, I hope, on what permafrost is. So where do we find permafrost then? Well, permafrost is basically underlaying most parts of the Arctic. If we look at the northern hemisphere, we have circa 25% of the land masses that are underlain by permafrost. And as you can see, it is in the Arctic here, but it is also in the high alpine areas. In addition to the permafrost that exists underneath the land masses, we also have permafrost underneath the Arctic Ocean. It is mainly on the continental shelves where we can find permafrost. Permafrost is, unlike the other cryosphere component, like for example sea ice and snow, not very easy to detect. You can't just look at it and see if there is permafrost or not, because it is a temperature definition. And also, it is not as rapid. It doesn't have that big annual fluctuations, like, for example, the sea ice, which has new records every now and then. We don't really have the same new records. We have warming and things like that, but not really the same record type of thing. That is not the way permafrost works, basically. You were talking a little bit about the active layer thickening, and these are from many different parts of the Arctic. They basically show the same trend, that this layer on top of the permafrost that thaws and refreezes on an annual basis has become thicker. I think you said 30 centimeters, sorry. And that is something we have experienced, for example, in northern Scandinavia during the last 3 decades, that we have an increase in this active layer thickness from 40 to circa 70 centimeters now. So it's round about the same numbers as in Russia. This is mainly due to increases in air temperature during the summer that we have experienced in the Arctic, and it is also due to rain. If you got more rain, then that can affect the thermal regime of the ground. If we look at the temperatures, that's the second. When we look at how permafrost is doing, it's basically 2 parameters that we are looking at. One is this active layer, how much it thaws and refreezes on top of the permafrost, and the second parameter that we are looking at is the temperatures. We can actually measure them. And in general, throughout the Arctic, we have an increasing trend in the permafrost temperatures from 0.5 degree to 2 degrees during the last 3 decades. What we can see is that in some areas it is getting more warm and in others not. And of course, if you are down here in Dead Horse in Canada, isn't it? Yes? I think Whitehorse is in Canada. Dead Horse, I don't know. Is it Alaska? How embarrassing. We rewind, and you haven't heard that. Is that okay? Is that okay? So Dead Horse in Alaska now. So if we are down here -8 and go up to -6, that wouldn't really be, I mean, it does affect a little bit, but it doesn't do a major thing. But of course, if you are in Gulkana, which I know is in Alaska, Yeah, and goes from sort of -1 degree to +1 degree, then you no longer have permafrost. And of course, that makes a big difference. The changes we have seen in permafrost temperatures are mainly due to increases in snow depth in some area. The snow is extremely important because it is like a big down duvet in the winter that heats the ground. In addition to that, it is also, of course, affected by warmer air temperatures. This is projected to increase in the future. So the trends that we are seeing now is projected to increase in the future. Then, of course, so what? Permafrost is warming, it is thawing in the southern regions. Why should you, me, care about that? Yeah, I would like to try to tell you why you should care about it. So, when we have this active layer that becomes thicker, these white figures here should illustrate ice. There are ice lenses in permafrost. And unlike when the soil thaws, it doesn't really happen that much. But if you got ice and it melts, then of course there are spaces that needs to be filled. And what happens then? Well, we have a collapse of the surface, so we have surface subsidence. And if you happen to have infrastructure on top of this surface subsidence, then it is not really fun. Roads, not really nice to, well, you obviously need big vehicles to pass by roads like this. And then, of course, you have houses. And who wants to be the winner of the leaning house, you know? If your house is leaning even more than Pisa, then you're not happy, are you? But of course, you can always argue that there are 4 million people living in the Arctic, so why should we care about those? They're not that many compared to the rest of the world, are they? But of course, there are minerals, there are plenty of resources in the north that we want transported to the south. So we are dependent on this infrastructure, like, for example, to transport natural gas and oil from the Arctic down to more southern regions. This is an unfortunate pipeline. It should not be on thawing permafrost because, of course, this can lead to a natural disaster, and we don't want that. That is the one thing that you can try to argue why people should care about thawing permafrost. And the other one is that there will be more carbon available. And carbon, it's the same. If we used to have this part that is unfrozen, now we get this additional area here which is unfrozen, where we have carbon. And when I talk about carbon, I mean things like this, old vegetation. If you have a leaf that falls off a tree in a temperate zone, then it gets decomposed immediately. Not immediately, but it gets decomposed. When you have something like this in permafrost area, it gets frozen into the ground. So it is stored there for many, many, many years. But when the permafrost starts to thaw, then you can actually have access to this carbon. This is, by the way, my son doing field work when he was a kid, just for the record. People are out taking soil samples around the Arctic to try to figure out how much carbon we actually have got in the ground. And with all the data, hard work that people have been doing, they have concluded that we are up to 1,700 gigaton of carbon stored in the permafrost areas of the Arctic. So what is this equivalent to? It is more than twice as much of the carbon that we have in the atmosphere today. So it is a lot of carbon. So what happens when we have this warmer climate? Lars Otto was talking about the feedback effects. And for permafrost, this is the most obvious one. We have a warmer climate. The warming climate starts to thaw the permafrost, and we get this additional area where we have carbon. Because we have this carbon available, it can get decomposed. And when it gets decomposed, greenhouse gases are being emitted. They are being emitted either as carbon dioxide or as methane, and of course additional greenhouse gases to the atmosphere means that we get warmer climate yet again. And so it continues. So if we then have this, and we have forecasts for how much of the permafrost that is thawing in the future, wouldn't we very easily be able to calculate the numbers that Pam was after before, how much additional carbon emissions will we actually get from the thawing permafrost? Well, there are, of course, Mother Nature is never easy. It's a complex system, and to be able to calculate how much it is actually getting out in terms of emissions, you need to take into account, for example, changes in vegetation. Because in some areas where we have permafrost thawing, we have changes in vegetation. Maybe we will get more vegetation that can actually have a higher uptake of carbon, which will then result that we have higher emissions, but we also have higher uptake, for example. In addition to the changes in vegetation, you also need to look at what is going on with the hydrology when permafrost is thawing. In some areas, like this one in West Greenland, we have drying of ponds. So when we have permafrost disappearing, then this active layer, the upper top of the area, actually gets down, and you can have a new drainage pattern. And because you can have a new drainage pattern, these ponds can dry out. If in some areas we actually have the opposite scenario, that when we have thawing permafrost, if you have plenty of ice lenses that melts, then you have a collapse and you have a subsidence. And if you have this subsided area, then it will be filled by water eventually. And if it's been filled by water, then you have ponding forming rather than disappearing. And this ratio between ponding forming and ponding disappearing, we don't really know. But it does make a big difference to the emissions, whether we will have carbon dioxide emissions when it's dry conditions, or methane emissions when it is wet conditions. And of course, the methane emissions, as you know, are 25 times stronger than the carbon dioxide emissions. So it is very important. So it is a difficult question to answer, unfortunately. But there are models working on, including wetlands and vegetation, etc. So hopefully we will get there. In addition to the carbon storage on land, Lars Otto was also mentioning that we have carbon basically seeping out of the Arctic shelves. So subsea permafrost is emitting methane. And this is what is quite old now, a paper in Science from Natalia Shakova, who's working together with Igor that Lars Otto was mentioning. And those red dots are where they have been going with the crews, taking measurements of methane, also high up in the atmosphere. And out of these, they have concluded that there might be as much as 1,300 gigaton of carbon in the shelves. But these numbers are very insecure. There is a paper coming out. I was hoping that it would be out by now, because when you're publishing in Nature and Science, there is an embargo until you have published it. But there is an upcoming paper by Shakova et al. In Nature Geoscience very soon, which are updating the numbers from the paper in 2010, and they have actually increased. I don't know if any of you saw this paper that was published in Nature, Vast Costs of Arctic Change. It is where they combined how much potential emission there might be of methane from this East Siberian branch of the Arctic Ocean, and how much that could actually cost. And what they conclude from this paper is, for example, that economic impacts of warming is being ignored. Sort of. And they also conclude that $60 trillion from thawing permafrost, that would be the cost from the thawing permafrost of the East Siberian Sea only. And in my world, $60 trillion? is a fantasy number. But I think it is great that we are trying to calculate some sort of number of those changes. But 1 month later, it appeared in Nature that other scientists had reviewed all the papers, all the literature that actually existed for this East Siberian Sea, and concluded that the greenhouse change is likely to be more gradual because of a slow rate of heat penetration in the subsea permafrost. The proposed scenario is therefore unlikely. So, it's a good thing we have scientists that are reading each other's papers, I think, so that we can keep up to. But to come to some sort of summary and conclusion here, I would like to say that permafrost is warming and thawing in its southernmost margins. It will lead to damage to infrastructure, and that will be costly. It can potentially affect the global climate, and of course, that will most likely be expensive as well. I think it is extremely good, even though this paper in Nature, where they tried to tell you a number, what the actual cost would be, happened to be a bit wrong in terms of the fluxes or the carbon store. I think this is the way forward, because if we are going to provide policymakers with ammunition, you need ammunition to act. You need to say that, if we do this, we can actually, it will be too costly if we don't do it. So I think this is certainly the way forward, so that policymakers can act because it is needed. Thank you very much.
No, I'm standing. Yes, good morning. It really is a pleasure to be here, and thanks to all of you for coming. I'm going to talk a little bit about sea ice over the next 20 minutes or so. But before I start, I just want to make 2 remarks. First of all, if during my talk anything should be unclear, please interrupt briefly. I love to be interrupted, so don't worry about that. And the second thing, you don't have to write anything down. If you want to have these slides, just send me an email. I'm very happy to provide those. Sure. Okay, I've called this talk The Big Melt, which, as you will see, describes quite nicely, well, nicely might not be the right term here, what is happening in the Arctic at the moment to sea ice. And so what I thought I would do over the next 20 minutes is to start with a brief description of what happens to Arctic sea ice at the moment, so outlining the current state of Arctic sea ice. I will then briefly talk about why care, because Arctic sea ice seems to be a rather remote thing that many of us might not care about too much or might not have cared about too much in the past. The third thing I would like to discuss briefly is why Arctic sea ice is melting, and the fourth one will be what the future will bring. The current state of Arctic sea ice, maybe it is a good idea to go back a couple of decades to the summer of 1979, which is the first summer for which we have reliable satellite estimates of Arctic sea ice coverage available. And what you basically see is that the entire Arctic Ocean is covered by sea ice. And to those of you who are not familiar with sea ice is nothing but frozen seawater, so it's frozen ocean water. It's normally between 1 and 3 meters thick. It floats around in the ocean. Some of it floats out here to the south in the Arctic. Some of it melts in the summer. So it's a relatively thin stuff. And because it is so thin, it very quickly reacts to climatic changes. And so it was taken as a warning call that within 26 years, from summer 1979 until summer 2005, we had lost roughly 4 times the size of Poland in terms of sea ice coverage in the Arctic. And this loss over 26 years was called dramatic by the media. And being a scientist, I'm not a big fan of this term dramatic, because I find it very hard to make that term even stronger to describe what happened over the next 2 years, from summer 2005 until summer 2007, when within just 2 years we again had lost 4 times the size of Poland in terms of sea ice. Summer 2012, again down 4 times the size of Poland. So this is where we were last year. In terms of aerial coverage, this is about half as much ice left as we had a couple of decades ago. In terms of thickness, which you can't see from this picture here, the ice has also thinned by roughly 50%. And if you so want to calculate the volume, for those of you who still remember the math at school, if you want to have a volume, you have to know the area and the thickness. And if both the area has decreased by 50% and the thickness has decreased by 50%, it turns out that what we have left in sea ice in the Arctic today is about a quarter compared to what we had 3 decades ago. So we have 3/4 of sea ice less in summertime compared to a few decades ago. And if you extrapolate that into the future, it is not difficult to imagine that the Arctic Ocean might look like this in summer within a couple of years or decades' time. And much of our research at the moment focuses on the question, how likely is it that this scenario will happen? And if it will happen, when will it happen? And I will come back to that question towards the end of my talk. For those of you who don't like images but who like graphs, here's basically the same information drawn as a line graph. So this is sea ice coverage in summer in the Arctic from 1953 until 2013. And you basically see this very rapid decline over the past few decades. And as a scientist who also does climate modeling other than doing fieldwork myself, it is a bit worrying maybe that the sea ice in the Arctic currently is retreating much faster than most model projections are saying. And again, I will come back to the question as to what we can learn from this difference towards the end of the talk, because often this is interpreted as saying that models are either wrong or too optimistic, but maybe the situation is a bit more complicated, so we'll come back to that later on. And that was basically all I wanted to say over the current state of Arctic sea ice. So what I hope you've taken away from that is that Arctic sea ice is disappearing very, very quickly at the moment. And we are very certain about that because we are observing it. The second point then is, of course, should we care? And if so, why should we care? Because the Arctic sea ice is relatively far away, so it might be some polar bears care about it, but why should we possibly care? So let's start with the first one, which is so-called polar amplification. And this term polar amplification simply refers to the fact that the polar regions of the globe, and in particular the Arctic, is warming at an amplified rate compared to the rest of the globe. And there's been a paper a few days ago which says that the Arctic is warming much, much faster, about 8 times as fast as the rest of the planet at the moment. Previous estimates were at a rate of about 2 or 3 times as much a warming of the Arctic compared to the rest of the globe. And some of this polar amplification, not all of it is as often put, but some of it is caused by the fact that sea ice is retreating. So at the moment, the Arctic is cooling itself very efficiently, or still very efficiently, simply because in summertime the sea ice reacts like a big mirror. So when sunlight comes onto the ice, it is simply reflected back into space, and that sunlight that is reflected back into space doesn't warm the Arctic because it's no longer in the Arctic. And if we now melt this mirror, if we make the sea ice smaller and smaller, more of the sunlight is being absorbed by the water, and this sunlight warms the water and leads to this amplified warming of the Arctic. And this is something that we see in observations, this polar amplifications. This is something that we see in model simulations in the past, and we also see it in model simulations of the future. So what is shown here is for the 3 scenarios that we've talked about before. So a scenario with little greenhouse gas emissions, medium greenhouse gas emissions, and large greenhouse gas emissions. The possible warming until the end of the century between 0 and 11 degrees centigrade. And you see that independent of scenario, it's always the Arctic that warms strongest. And this strong warming of the Arctic leads to this, is in part caused by this retreat of sea ice. And obviously, because this island called Greenland is centered in the Arctic, or is located in the Arctic, the loss of sea ice that causes this amplified warming contributes to the increased surface melting in Greenland that we've seen over the last decades. Here's, for example, a snapshot from July 2012. And everything that is red in this figure means that the surface of Greenland is melting. And this is a rather unusual picture in that the entire interior of Greenland is red, which means that in the last year, for the first time in many, many decades, all of Greenland's surface was melting, and that is in part because the Arctic is warming so rapidly at the moment. And obviously, Greenland is ice that is sitting on land, and if this ice melts, or if icebergs fall off this land, and they fall into the ocean, global sea levels rise. So indirectly, because of this polar amplification, the retreat of sea ice causes increased melting in Greenland and hence increased sea level rise. A third factor that also Lars Otto Ryerson briefly mentioned is the fact that this sea ice up there, when it retreats, it changes atmospheric circulation. So what is shown here is a map of the Arctic for January 2010, and the colors simply indicate if a region is warmer than normal or if it was colder than normal. And what you see here is we have Svalbard here, that much of the interior of the Arctic, and in particular Greenland, is much warmer than it normally is in January, whereas much of Central Europe and Siberia, Asia here, is much colder than it usually is. And model studies have shown that this is probably in part caused by the fact that we've lost a lot of sea ice in this region here. And so what happened in wintertime, that in this region no longer cold sea ice was in contact with the atmosphere, but the warm ocean was in contact with the atmosphere. And the ocean provided a lot of heat to the atmosphere in this region, and that changed the atmospheric circulation in a way that brought cold air out of the Arctic into our latitudes and warm air from down south into the Arctic. And I can vividly remember in January 2010, we were doing field work here in the west of Greenland, and we were hoping for sea ice to form. And there was normally forms in October in that region. And there was no ice in October, no ice in November, no ice in December, no ice in January, no ice in February. Some ice finally formed in March. And so we were just sitting there with all our instruments, and all the time the Baltic Sea was frozen. So next time we just go to the Baltic Sea and do our field work there. And then another example in January 2012. Some of you might remember that in January 2012 we had snow in Portugal, we had snow in Greece, we had snow in Poland, we had snow all over Central Europe. And I was sitting in Spitsbergen, it was plus 7 degrees and it rained. And so what we really see here is this strange change in weather patterns that in part is caused by this loss of sea ice. A fourth factor, because the sea ice in the Arctic is retreating rapidly at the moment, it becomes more and more possible to get to the ocean seafloor. And at the ocean floor, it seems very likely that there's a lot of oil and gas still to be extracted. And about some estimates say that about 25% of all the oil and gas that we haven't taken out of the ground yet is located here at the bottom of the Arctic Ocean, and because the ice goes away, we can get to that oil and gas. Whether that's desirable or not is not a scientific question, so I will not talk about that here. In terms of these oil and gas reserves, it's of course important to figure out whom these oil and gas reserves belong to, because they're worth billions and billions of dollars. And so any neighboring country of the Arctic here would like, of course, to have its share of these oil and gas reserves. And so in some of these regions, there is a bit of a conflict as to whom certain areas belong to. And even in areas where there is no such conflict yet, it's still not clear if some of these waters are international territories that belong to the entire human world, or if they are territorial waters. And that is something that depends on the geological properties of the seafloor here. And the issue is that a lot of the Arctic Ocean is bounded by shelves, and these shelves are normally taken as a natural extension of these countries bounding the Arctic Ocean. And so everything on top of these shelves belongs to these countries if they can prove that these shelves are simple geological extensions of their own territories. And so at the moment there's still quite some dispute on that. And all these things nobody thought about 20 years ago. And that is one of the things that I find quite striking about that in this very remote area where only a relatively few people are living, something is changing at a rate that we didn't expect, and suddenly all these problems come up. And if I extrapolate this, what happens in the Arctic now, to areas where millions and millions of people live, I often believe, and I'm very strongly convinced actually, that a lot of surprises are still awaiting us as to the consequences of climate change. A sixth issue, of course, of the retreat of sea ice is the fact that there's a lot of animal species living in the Arctic. The most famous one, probably the polar bear, but also smaller ones in the food chain like the ring seal or some krill. And all these species will be affected one way or the other by the retreat of sea ice. But there's not only animals living there, of course, there's also humans living there for millennia. And I had the chance to talk to some of these people when we did fieldwork in Greenland, and one of them put it quite nicely in saying that for us, coming from warmer regions, sea ice is a frozen ocean, but for the people who live out there, it's rather the contrary, that for them a liquid ocean is melted sea ice. So the normal state of the ocean has always been, it's frozen. And then every now and then in summer it does this weird thing, it melts. But for them, for example, in the year when we were doing our fieldwork in Greenland, these people couldn't do their traditional hunting on the ice with their dog sledges when they went hunting for seals. So what they did instead, they just went fishing all winter long, and they're telling us that they don't need the dog sledge teams anymore because it's expensive to feed the dogs, and since there's very little sea ice left, they don't need those anymore, so they get rid of those. They change their lifestyle to just go fishing. But when they do that, they now suddenly catch fish for which they don't have names because the water has become warmer, so new species come into these regions. And once they've caught these fishes, they can no longer dry them in the air as they used to do because insects are coming that didn't used to exist there. They put their eggs into the fish and the fish rots. And so these people are very, very directly, very strongly affected by these changes in the sea ice cover as we speak. And the final one, a bit more personal, being myself in the Arctic basically every year, I've really, really fallen in love with that landscape. And it makes me, especially when I'm up there, really sad to imagine that my kids, which are like very, very small at the moment, when they've grown up, they probably can't go up there and see these landscapes anymore. So there are entire landscapes disappearing from our planet at the moment. And that personally, not as a scientist, but really as a human being, makes me sad because I find these landscapes extremely beautiful. And I think it is important for us humans to have these landscapes that are simple nature and they're largely unaffected by human activities. Why is Arctic sea ice melting? That is, of course, a very, very important question. And to put that a little bit into context, I've put up this figure here, which shows the temperature evolution over the past 50,000 years. And what we see from that graph is that climate change is nothing unusual. Climate change has always happened, will always happen. What is unusual, though, and this is temperatures in Greenland here, is that for the past 10,000 years, the temperatures on this planet are incredibly stable. And that is because the Earth rotation around the sun is relatively circular at the moment. And it's these 10,000 years of a rather stable climate that we humans have used to develop our civilizations. And everything that we have in terms of infrastructure, in terms of crops, in terms of cities, in terms of coastlines, all that is very, very well adjusted to these 10,000 years of stable climate. And what we need to find out now is whether or not we humans have started to make an end to this stable climate and to move into a climate that is warmer than what we had for the last 10,000 years and that is warmer than anything that humans have ever experienced. And it is therefore important for us to find out why is the Arctic sea ice disappearing. And now there are three reasons for why the Arctic sea ice could be disappearing, or three main reasons. One could be related to something that the sun is doing. It could simply be bad luck. Stuff just happens in the climate system. Or it could be CO2. And let's just take quick looks at each of these things individually. We know from the past that, for example, 5,000 to 8,000 years ago, we had less sea ice in the Arctic, and that was because the Earth axis was tilted in a way that we got a little bit more solar radiation in the Arctic back then. So we know that there was less ice back then because of something the sun did or the Earth did instead. We know that in the 1930s, we had less ice in the Arctic, not as little as we have today, but regionally a decrease in sea ice. And we are pretty certain that there's just natural variability, that the ocean currents were a bit different back then and then changed back to their normal state. So we know that the sun and bad luck had something to do with sea ice loss in the past. But let's look at the present. Let's look at the sun, for example. And in particular, let's look at the solar activity, which is shown here, and the red is sort of the 11-year mean, which gets rid of all these big excursions. The sun has become weaker over the past 10 years. And it's very, very difficult for us to figure out a mechanism by which a weakening sun melts sea ice. If anybody has any idea how that could work, please let me know. I'd be very interested. But until we have any of these ideas, we would normally suggest that if the sun is a main driver of what happens in the Arctic, the ice should be expanding. So the solar irradiance has weakened in recent decades, and hence it is very unlikely that the sun is responsible for the ongoing melting of Arctic sea ice. The second thing, bad luck. While Arctic sea ice comes and goes, so it always comes and goes, up and down, we can estimate both from observations and from modeling activities what the sort of range of variability would be for modern climate conditions. And it's basically this yellow region here. And we see that a lot of what happened in the past is explicable simply by these ups and downs, that summers are sometimes cold and summers are sometimes warm. But basically everything that happened over the past 10 years is no longer explicable by internal variability, because the downward excursions are simply too strong. And so natural variability cannot explain the full magnitude of the ongoing melting of Arctic sea ice. It is likely that it has contributed to the very rapid loss, but it is definitely not the major driver. Which brings us to CO2. And what I've shown here, to start that quickly, is a model simulation of how sea ice in a model simulation evolves from 800 until 2100. And that agrees for the time where we do have observations relatively well with the observations. And now you might wonder what we did in our model to make the ice disappear so rapidly. Well, we did two things. First of all, we told the model what the sun is doing, and that caused actually a very slight increase in sea ice here over the first 1,200 years or so. And the second thing we told our model is how CO2 was changing. And I've plotted this curve upside down here, and you can't see it for reasons that I don't quite understand. It's probably on that little screen, but not on the projector. So if you would see it, you would see a line that would go like that, and then we started to increase CO2 after the Industrial Revolution, and it basically matches the observed sea ice evolution perfectly. And so from these model simulations, we see that CO2 is a main driver of what happens to sea ice. Now you could say, well, it's just a model, but we see exactly that same relationship in the observations. So what is shown here is for every year since the 1960s is a dot for that particular year, how much sea ice we have and how much CO2 we have. And in the 1960s, we had a lot of ice and relatively little CO2, and then each of these dots is a new year. And you see as time goes by, these dots move to less sea ice and a larger CO2 concentration. And so both in the observations and in the models, we see this very, very strong relationship between CO2 evolution and sea ice evolution. And that brings us to stating that the increasing CO2 levels have very, very likely a major role in what happens to Arctic sea ice at the moment. Finally, what will the future bring? What I've shown here is a plot of an estimate how sea ice volume has changed over the past 30 years. It's a model simulation that is sort of constrained by observations. And these observations, summer sea ice go down from 18,000, I don't have the label here. So this is 18,000 cubic kilometer, I apologize for that, 18,000 cubic kilometer, and now we are down at 4,000 cubic kilometer. And if you go online, you will find lots and lots of web pages that would just draw a line through that and tell you, well, we'll be down to zero by 2015 or 2016 or 2017. Now, these drawing lines and extrapolating into the future is not really the most advanced scientific method that we have. And that drawing a line method is a little bit based on this feedback loop that we briefly discussed before, that we have less sea ice now, which means that we absorb more solar radiation in the Arctic Ocean, so we get warmer water, which means that we get less sea ice, and so on and so forth, and so the thing will just go down until all ice is gone. And this feedback loop is often referred to as a tipping point, especially in the public media. So there's all these snippets here. Arctic sea ice faces rapid melt at tipping point, enters death spiral, and so on and so forth. If we look at that a little bit with a bit of a distant eye, and we look, for example, as to this rapid retreat we had in 2012. If this feedback loop really would be strong, after a year where we get rid of a lot of ice in the Arctic, you would expect that next year there should be even less ice. But that didn't happen. In 2013, the ice recovered a little bit. And we actually saw that in the past again and again and again. Whenever the ice decreased very rapidly, it recovered a little bit in the next year. Decreases rapidly, it recovers a little bit. And that we also see in models, we see that in observations, and that tells us that this ice albedo feedback loop, it exists, but it is not strong enough to sort of drive the ice into nothingness by itself. And the reason for why the ice always recovers a little bit is basically twofold. First of all, in these regions where we do get rid of a lot of ice in summertime, in winter we have this warm ocean in contact with the atmosphere. And here we have a lot of heat exchange from the ocean to the atmosphere, so we very efficiently get rid of all the heat from the ocean, put it into the atmosphere within a few weeks, and you see that as steam over the Arctic Ocean. And so we very rapidly form sea ice again in these areas. And once we start forming sea ice in these areas, the ice very quickly grows, and that is shown by the blue line here. So we compare here, red line is ice that survived a certain summer melt season, and the blue line is ice that only starts forming from open ocean in November, for example. And because ice grows by heat being extracted from the underlying ocean and put into the atmosphere, ice grows much more rapidly when it's thin. And therefore, this blue curve rises much more rapidly than the red curve. And it also helps this thin ice that there's less snow on top because it formed later and because the snow is insulating. And so therefore, in our model simulations and also in the observations, the ice always recovers a little bit after these massive drops. And that makes it, at least from a climate modeling perspective, relatively unlikely that the sea ice in the Arctic will be gone within 2, 3, 4, 5 years, as you see in the internet. And I've shown this here, for example, the black line is observations, the green lines are model the green, red, and blue lines are model simulations. And for example, this green line here is one of our model simulations, follows the observed one relatively closely, but it shows no sign of going down any further. And this graph is actually quite interesting for a different reason as well. So what you see here in the 3 lines, these are all simulations, all with the model from the Max Planck Institute in Hamburg that we run. All these models get the same information, so it's all the same model. So all these simulations get the same information about what the sun did, what the CO2 did, and so on and so forth. And we then start the model in 1850 and let it run. And what we actually find is that in one of the simulations over the past 30 years, the sea ice is slightly increasing. And in one other, it's decreasing as fast as has been observed. And that is basically the range that the climate models tells us that is the range that is plausible. And then which of these ranges the actual world picks, that is then what we refer to as internal variability. And so you can't tell much about the quality of a model by looking at how good does this model, this climate model, match the observed evolution? Because the climate model doesn't know about what happens just now. It starts in 1850 mostly, is then integrated forward in time, and it's just being told this is what the sun does, this is what CO2 does, this is what volcanoes do. And some of these simulations, simply because weather is a chaotic thing, show the ice cover is slightly increasing, some show a strong decrease. And that is basically this range that we do get from the climate simulations. And so to end, I'll tell you what happens after 2030 in these simulations. What will happen in the future depends very much on our CO2 emissions. And so so the blue is the past evolution in the model. In this green scenario, which is the 2.6 watt per square meter scenario, summer sea ice drops a little bit further and then recovers slowly. But in both the 4.5 and in the 8.5 scenarios, so these little bit stronger scenarios, Arctic sea ice disappears until there's nothing left in summertime. And so if we believe these model simulations, it basically tells us if we want to keep summer sea ice in the Arctic, from a scientific point of view, that is still possible. From a political point of view, it means that we need to follow the RCP 2.6 scenario, which in practice basically boils down to the very simple thing, very simple to put, but very hard to do, is to just agree as humans that 80% of the known oil, gas, and coal reserves we will leave in the ground. And that is basically the one number that I think is discussed far too little, that it's just 80% that needs to stay in the ground. We don't need to burn it. That is RCP 2.6. And I'll leave it to each of you to decide how likely that is going to be. To summarize, changes in Arctic sea ice are the rapid alert system of global climate change because it's easy to detect and it changes very rapidly. The observed changes are very likely primarily caused by increasing CO2 concentrations in the past, which means for the future that the future evolution of Arctic sea ice depends on future CO2 emissions. And a rapid loss of summer sea ice within this decade is possible, but according to what we know from climate models, it is very unlikely. Thank you very, very much for bearing with me, and I'm very happy, and the others are as well, to take questions. Thank you.
So we do have time for some questions for all three of these speakers now. So I'll again be the microphone runner. Yeah.
I got a question for Dirk. Yeah, my name's Andrew. I'm with a group called Sustain US over at the UNFCCC conference. So I was sitting down last night. I was reading about a research team that went out to Baffin Island, and they were measuring the level that let's see. They were measuring the snow level that had increased from, let's see, from 120,000 years ago at the end of the Eemian, I believe. And they showed that there was a 2.7 degree decrease in temperature from that time, I believe, in that area. And that models from the CMIP5 had showed a 1.1 degree decrease. And the conclusion that they ended up coming up with was that we don't really have a good understanding through models of the Arctic amplification effect. So I was wondering if you could address that at all.
Yes. So to rephrase the question as I see it, it's basically a model's failure has been reported to simulate the evolution of the Arctic over the past 130,000 years or so. And I would immediately believe that. So we do have relatively little understanding, or comparably little, we don't have sufficient understanding, to put it like that, to really model the climate on these long time scales. And there are a couple of initiatives on the way to address that shortcoming. Regarding the more recent evolution of the Arctic, climate models have again and again shown a surprising amount of skill to get the Arctic amplification modeled comparably well compared to observations. And so the figures that I've shown here, where we've compared, for example, our model to Arctic sea ice evolution, if we do the same comparison for temperature, for pressure patterns, and so on and so forth, the model simulations match very well with what has been observed. And why I put more weight to that compared to what happened over the past 100,000 years is not only that we have little understanding from a modeling point of view, but we also have little understanding from an observational point of view as to how reliable and how robust these observations are. And so at the moment, I would say that the skill in representing reliable observations with our modern climate models for modern climate conditions is sufficient from a policy-making point of view. But obviously, we do have shortcomings when it comes to sort of 100,000-year timescales.
I'm Svante Bodin from ICCI, and also have a question for Dirk, actually. And it's more about the modeling here. When you, in your slides, refer to CO2, do you really mean CO2, or do you mean all long-lived greenhouse gases? That is the first part of the question. The second part is actually in the Max Planck Institute model. Do you also model the full aerosol cycle and atmospheric chemistry as well? So it's not only the long-lived greenhouse gases, but also impacts of aerosols.
So when I refer to CO2, in the two slides where I looked at when I refer to CO2 in the observations, I meant CO2. So we do see a very strong relationship between CO2 and sea ice in the observations. In the modeling world, and you're very right, and thank you very much for proposing that question, we don't only prescribe CO2, but really all long-lived greenhouse gases. Regarding the second question, as opposed regarding atmospheric chemistry, all the simulations I've shown here were from the standard CMIP5 simulations, and in these simulations, the aerosol load is simply prescribed. So we tell the model, this is what the aerosol does and will do in the future, this is what CO2 did and does, and this is what methane did and does. And the model then just takes these as boundary conditions and simulates what the climate will do to these prescribed forcings.
I'm going to ask a quick question. Actually, it might not be a quick of Margareta. And that is that for the On Thin Ice report, I need to say that one of the things that we struggled the most with towards the very end of the report, it's probably the last thing that we changed, was how to talk about the risk of methane and CO2 release from permafrost. And finally, we simply followed AR5, which says that there's a potential for a doubling of the contribution by 2100. But you know, given the controversy over the study that came out this past summer, and I know there was an answer actually to the letter that you cited where they said, well, if you spread it out, the cost is actually more. It's just more over a longer period of time. So there's a lot of debate. How would you characterize that risk if you could control the On Thin Ice report?
I think the simple answer is that I couldn't. Unfortunately, I mean, I wish I could, but I mean, and I think, as I pointed out, I think it is extremely important to have exercises like this when you have economists working together with natural scientists. But I think the problem was maybe not the economists so much as the input of carbon that they thought was going to be released. That is the part that is being debated by the science, the natural science people at least. So again, but I mean, we don't have the answer.
Maybe just to add on that, because in addition to that letter from Lund, we also wrote one also criticizing this initial study in Nature. And one of the points that they failed to make is they say in this article in Nature that this is a likely scenario, and they actually quote Shakawa on that. But if you look into the original publication, Shakawa herself says, we don't know. We have too little information to quantify that. And so there's too little information to quantify that made it into this is a likely scenario. And that is, from a scientific point of view, something that we should criticize, I think. Yeah.
Well, I'm Frank Martin Seifert from the European Space Agency. And since 3 years, we have a cryosat in orbit that is a satellite specifically measuring the extent and the thickness of sea ice. And I confirm what Dirk was saying, that we are seeing during the last years that the sea ice not only is shrinking in extent, but is as well diminishing in its thickness. Together with other space agencies, since 40 years, we are trying to do systematic observation of the cryosphere, not only of sea ice, and we will continue with more satellites to give you, as input towards the models, the necessary data that the models get better error bars and are more secure, to convince our politicians to do something about the Arctic.
Yes, thank you for this statement, and it is almost impossible to overstate the importance of improved observations from basically all perspectives. So we are very, very grateful for all these initiatives. Thank you very much.
It's about time for coffee. We have time maybe for one more quick question. Okay, so we'll break now for 15 minutes, and then we're going to do a bipolar world. We're going to jump from the Arctic to Antarctica for the next session. Thank you.